Hi, meet me again. Okay, here now for this particular video, I want to teach you guys about the friction. Okay, dry friction especially. Okay, how can we solve problem which involving friction? Okay, uh, let me share my screen. Okay, so for today, we will concentrate on the basic theory of the friction. Okay, especially the dry friction. So I believe you have learned about this for quite a while. Okay, I believe it's from high school or even in secondary school as well. Okay, so when we talk about friction, okay, if you have something like this, okay, if you have something like this, if you have a square block or something like this, okay, then after that you pull it with force P, okay, and because of there is a contact between the block and the bottom surface, okay, there will be a friction there. Okay, there will be a friction between the block and the bottom surface. Okay, and if we draw the free body diagram as usual, if we draw the free body diagram and if we assume that the block has, for this case, the block has to be is supposed to have a mass. Okay, so there will be a force downwards, the gravitational force downwards, mg, due to the mass. Then there will be a normal force which resisting the gravitational force mg. It will be the n normal force there. Then there will be a friction which in the opposite direction of the impending motion and the motion as well. Okay, so in this case, because the block is pulled by force P to the right, the friction force will be going to the left. Okay, something like that. I believe you have learned about this before, way before I teach you guys about this. Okay, but for today, I will just want to like refresh all the things that you have learned up until now. Okay, and maybe some of those something that you that are quite new, I will discuss about it, but not in this video, because for this video I believe all the basics you have learned it before in last year physics, okay, and in your high school year as well. Okay, the things that you need to know is the value of the friction force that can be there. Okay, you have to remember that if one thing is contact with another thing, there will be a friction force between those two, and the friction force will depend on the one of it on the mu. Mu is the friction coefficient. Okay, the friction coefficient, and you have to know that we have two friction coefficient. The first one is static friction coefficient, and the second one is kinetic friction coefficient. Okay, let's go to the next slide. Okay, something like this. This is the same thing as what we talked before. If we have a block like it, and I want to compare between the force, the pulling force P, and the friction force. Okay, and I want to how to say that? I want to draw it in a graph like that. Okay, the friction force, the value of the friction force when the P is keep going up like that. Okay, so this is sorry. This is for example, right? If I keep pulling it with higher and higher force, so P, I keep increasing the P values. Okay, you can see there that the friction will increase as well at the same time, because friction F, the friction force F, is the one which resisting the P. Okay, it's action and reaction with the P there. But it can only holds until certain value, the friction force. It can only holds until certain value. There will be a maximum friction force which is available. Okay, and the maximum friction force there, it's supposed to be the same as our normal force. Okay, normal force multiplied by the static friction coefficient μs. Okay, then if we keep increasing the pulling force P, okay, at certain time the pulling force will be greater than the maximum friction force, maximum possible friction force. In that case, what will happen after that is the block, which at the beginning it stays stationary. Okay, the block will starts to move. Okay, it starts to move. Okay, and it starts to move because the sigma f is not zero anymore. The sigma fx, especially in this case, is not zero anymore. That's why there will be an acceleration in the x direction, in the direction of the pulling force P. Okay, when it happens, right, the friction force actually will drop a bit, because when the movement happen, when the movement happen, we can't use static friction coefficient anymore. We have to use the kinetic friction coefficient, which is mu k. Okay, and the value of mu k is normally slightly lower, or lower than the mu s, the static friction coefficient. That's why normally the friction coefficient, when it starts to move, the friction force will drop as well, because then at that time the friction force will be the same as the normal force multiplied by mu k, or kinetic friction coefficient. Okay, so this is the animation when it starts to happen. So the movement starts to happen because the equilibrium is not happening. Sigma fx is not zero anymore. There will be an acceleration, and it's because of the P is bigger than the F. Okay, that's why the sigma fx there, P minus F, will become our mass multiplied by acceleration. So the acceleration will depend on this one. Okay, that's the thing. So let's try to explain about it, and let's try to elaborate more about this. Okay, you can see here in this graph. Okay, actually it shows us, right, whenever we have a pulling force, the free body diagram is the same as before. Whenever we have the pulling force, okay, until certain friction force, okay, the friction force will still exactly the same as the pulling force. Okay, it will stay the same as the pulling force. Okay, until it reaches a certain value, which is the F max here, the mu s multiplied by normal force. Because at this point, okay, this point is the maximum friction force available. It can't go any bigger. Okay, so the friction force is supposed to be the same as the maximum friction force, or lower than that. Okay, if the pulling force in the previous free body diagram is lower than the maximum friction force, at that time, okay, the block will stay stationary. Okay, the block will stay stationary, and the friction force, the value of the friction force will be the same as our pulling force P. Okay, will be the same as our pulling force P. So it is a big mistake. It is a big mistake if, okay, when it is stationary from the beginning, you assume that the friction force is always mu s multiplied by n. It's a big mistake. because the value will only be the same as mu s multiplied by n when the pulling force is the same value as the maximum friction force mu s multiplied by n. So if the pulling force is lower than this, okay, the friction force is actually not depending on this, but depending on your pulling force. It will be the same as your pulling force. Okay, so please try to fix that concept. If until now you still think that if one particular thing is in a stationary, okay, the friction force which is happening at that particular thing is mu s multiplied by n. No, it's a big mistake. No, it's wrong. Okay, the maximum friction force which is available for that thing, yes, is mu s multiplied by n. But it is the maximum friction force which is available. Not necessarily we have to use all the maximum friction force. Okay, most of the time we use lower than the maximum friction force. Okay, then if we keep increasing it, okay, if we keep increasing the pulling force, right, as I told you before, if we keep increasing the pulling force and it is higher than the Fmax friction force, maximum frictional force, higher than mu s multiplied by n, in that case, movement will happen. Okay, it will accelerate, and because of that, because it's already moving, okay, we have to use the kinetic coefficient of friction. Okay, kinetic coefficient of friction, or mu k. Okay, which the value is lower than our mu s. And at that time, our frictional force will be like this, the same as mu k multiplied by n. So this value will be correct if the condition is your the things that we studied about is in movement. So it's moving. If the things that we study about is moving, okay, the frictional force that we have to use is this one. Okay, so there's supposed to be a relative motion between the ground, okay, between the ground and the things that we studied about. If there is a relative motion between those two, yes, we have to use mu k instead of mu s. Kinetic coefficient friction instead of static coefficient friction. Okay, and your frictional force will be like this, mu k multiplied by n, if there is a movement. Okay, and this is the graph. Okay, if there is a movement, the frictional force will drops, and we have to use mu k instead of mu s. Okay. Yeah, this one I already explained to you that mu k is always, normally, not always, but normally is lower than mu s. Okay. Yeah, this is I already explained to you as well. That frictional force when there is no slipping, when there is no movement, okay, the value can be anything from 0 to Fmax, and it will depends on your pulling force P. Okay. Sorry. Okay, and when the frictional force reaches the maximum value, or mu s multiplied by n, in that case, we have special terms for that. When actually, when we calculate everything and actually the frictional force that we have is the same as our maximum frictional force, or the same as our mu s multiplied by n, okay, in that case, the condition that happened to that things that we study about is impending motion, which means that the motion is about to start. The motion is about to happen, impending motion. Okay, so based on the things that we have studied up until now, there are three conditions. Whenever we deal with a frictional force, whenever we deal with a friction, there are three conditions. Okay, three conditions which we can analyze. the first condition is quite easy as well. The first condition is quite easy. The third condition is quite easy. The hardest one is the second one. The first condition is if we know, okay, from the problem, it's clearly stated that impending motion is known to exist. If impending motion is known to exist from the problem, or we know it already, if impending motion is known to exist, we can directly use this. The frictional force is the same as our maximum frictional force, which is the same as mu s multiplied by n. Static frictional force, static coefficient of friction multiplied by the normal force. Okay, that's the first condition. It's quite easy. Okay, but you have to make sure that it's clearly stated in the problem that impending motion is there. Okay, impending motion is known to exist. Okay, then the second one is quite hard. That's why I will skip it. Okay, the third one is easy as well. Okay, it's known as well. The third condition is known. Is if it in the problem, it is known that slipping is occur. Okay, slipping is there, which means that the things is in a relative motion with the ground or with another thing. Okay, if we know that slipping is there. Okay, we can use it directly as well. That the frictional force is supposed to be the same as our kinetic frictional force, which is the same as mu k multiplied by n, normal force multiplied by the kinetic coefficient of friction. That's the third one. The first one, impending motion, is known to exist. The third one, slipping, is known to exist. Those two are easy. Okay. Now the second problem. The second problem is the hardest one. Okay. If there is no information in the problem, okay, we don't have any information at all in the problem. Okay, we don't have any information at all in the problem. Okay, because if we don't have any information at all in the problem, there are several possibilities. Okay, there are several possibilities. Three possibilities. If F, the frictional force, is less than the first possibility is if the frictional force is less than the available frictional force or the available maximum frictional force. Okay, that's the first condition. If that's the case, then it will stay stationary. Okay, it will stay stationary, and we have to draw the free body diagram, and the frictional force is supposed to depend not it's supposed to depend on the forces happening at the free body diagram. Okay, in the previous free body diagram, which is that simple, it will depend only on the pulling force, but most of the time it will not only depends on the pulling force. That's the first case. The second one, if when we calculate the frictional force, okay, we calculate the frictional force and the value is the same as Fmax. Fmax or our mu s multiplied by n. Okay. By doing so, we know that the our free body diagram still accurate. Free body diagram is accurate, and the result is accurate as well. Okay. The third one is if our calculation of a frictional force from the free body diagram is bigger, okay, bigger than the Fmax or maximum frictional force or mu s multiplied by n. That's the third one. Okay, if it's bigger, if F is bigger than the maximum frictional force, it will not be possible. It will not be possible. Why it will not be possible? Because the maximum available frictional force is only Fmax, only mu s multiplied by n. So our frictional force can't go higher than that, can't go higher than maximum frictional force. In that case, means that our free body diagram is totally wrong. Our free body diagram is totally wrong because our F will not be possible to be bigger than Fmax. In that case, we know that motion is happening. motion is happening. That's why we have to replace our F there with Fk, okay, kinetic frictional force, mu k multiplied by n. This one, mu k multiplied by n. Okay, then after that we can calculate the acceleration. Okay, so the equilibrium will not be maintained there. Of course, equilibrium will not be maintained there because there will be acceleration. The sigma f will not be equal to 0 because there is a motion there. Okay, so that's the hardest case, the second one. If we don't have any clue about whether impending motion happening, or whether the slipping happening, or whether it stays stationary. Okay, in that case, we have to draw the free body diagram. Okay, for the second case here, what you're supposed to do is we draw the free body diagram, assume the friction as of F frictional force, then calculate everything. Okay, and there are three possibilities there. Okay, this one, three possibilities there. If F is less than the maximum frictional force, mu s multiplied by n, then our free body diagram is correct. The calculation is correct. Okay, then if F is the same as maximum frictional force, is our frictional force is the same as maximum frictional force. Okay, our free body diagram is still correct. And equilibrium is still maintained. So our results is still correct. Then the last one, if the F is higher, if our frictional force, our calculated frictional force is higher than the maximum frictional force of mu s multiplied by n, in that case, we know that it will be slipping. And we know that the equilibrium will not be maintained because it's not possible. So in that case, we have to replace our F, we have to recalculate again and replace our frictional force with kinetic frictional force, which is the same as mu k multiplied by n. And then we can calculate the acceleration. Okay, actually that's the theory behind it. Okay, and I think some of you may understand OAD because it's just a review of the things that we have learned up until now. But maybe some of you have difficulties on this as well. That's why I think it is better for us to practice with some of the problem example. Today, I will discuss two problem example. Okay, the first one is this problem example. Try to read the problem example by yourself first. Then after this, I will explain to you how to solve this particular problem. Okay. So basically, the problem that we are trying to solve is this kind of thing. Okay, there is a block. The block is actually stays stationary in a slanted ground. Okay, slanted surface like this, and the surface has an angle of 20 degrees to the horizontal to horizontal line. Okay, and the P is giving horizontal. The P is given to the block horizontally like this. And there are two conditions of P. The first condition, A, condition A is the P value is 500 Newton. And the second condition, P value is 100 Newton. And we have to explain what is happening when P is 500 Newton. And we have to explain as well what will be happening if the P, the pushing force here, is 100 Newton. Okay, that's the question. Okay. Oh yeah, this one is, you have to determine the magnitude and direction of the frictional force acting on the block. So the direction and the magnitude of the frictional force. Okay, this problem example is actually our second case. Okay, second case means the condition is not known yet because there is no information about the condition, right? We don't know whether it is a impending motion. We don't know whether it's slipping. Okay, so it's supposed to be the second case. So we have to find it out by ourselves. In that case, we have to draw the free body diagram and assume all the forces happening there. In this case, the forces that will be happening here in the block, okay, if we isolate the block, okay, there will be horizontal P force there, and then there will be gravitational force due to the mass, and beside it there will be a frictional force in the direction of the surface of the ground surface, okay, and then the normal force as well, perpendicular to the ground. Okay, let's draw it. I think I will try to solve for problem A first. Okay, this is the free body diagram. As you can see here, there will be a W. The value of W is 100 kilograms multiplied by 9.81, okay, meter per second square. The value there is supposed to be 981 Newton going down. Okay, then the P is 500 Newton. Then normal force is going to Y direction. Remember, this is our X direction. X direction is parallel to the ground, and Y direction is perpendicular to the ground. Okay, so our normal force is supposed to be to the Y direction, perpendicular to the ground. Then the frictional force, in this case, I assume that the friction force is going up instead of going down. You can assume actually, because we don't know, right? In this case, we don't know the direction of the frictional force. It can go down or it can go up as well. Okay, so in this case, we assume that the frictional force is going up. Okay, then after that we solve it like this, right? 500, 981 going down, normal force, frictional force. Okay, in this case, we have two unknowns, N and F, right? The frictional force F and the normal force F. Hey, I'm sorry, I show the solution first. There are two unknowns, N and F, okay? And because it's a point equilibrium, in this case it's point equilibrium, because we don't have the dimension, point equilibrium, we can only use two equations only, sigma fx and sigma moment. In a point equilibrium, there will be no sigma moment equal to 0. Okay, only sigma fx equal to 0 and sigma moment equal to 0. Sigma fx equal to 0, what we have there will be F there, F will be there, 500 Newton cos 20 degrees will be there, 981 Newton sin 20 degrees will be there. Something like this, okay? 500 cos 20 degrees plus F, okay? Going uphill is positive, minus 981 multiplied by sin 20 degrees equal to 0. That's the first equation. The first equation. The second equation is from the sigma fy equal to 0. Okay. Sigma fy, what will be there will be this one, 981 cos 20 degrees, 500 Newton sin 20 degrees, and normal force. Okay, something like this. Okay. So N going up is positive. N minus 500 sin 20 degrees minus 981 cos 20 degrees equals 0. Two equation, two unknowns, we can solve it. N and F. Okay, the normal force value is 1093 newtons, which means our normal force is correct. The direction of the normal force is correct. Then the frictional force is minus 134.3 Newton. And minus means the direction is wrong here. It's supposed to be going down instead of going up. It's supposed to be going down instead of going up. Then we have to analyze it because we don't know whether this result is correct or not. Remember, when the second case happening, when we don't know what is happening in the block that we analyze, okay, or the things that we analyze, okay, we have to know which case is happening to our thing. The first one, it can be impending motion. The The first one, it can be just stationary, normal stationary. Okay, the second one is impending motion. Motion starts about to happen. The third one is motion is already happening. Okay, we have to know which condition is happening here. We can check by calculating our maximum frictional force. The maximum frictional force is supposed to be the same as our normal force multiplied by mu k. Okay, sorry, not mu k, mu s. Static coefficient of friction. Remember from the problem, the static coefficient of friction is 0.2 and the kinetic coefficient of friction is 0.17. So in that case, we can continue. Okay, we have to check whether this frictional force here, 134.3 Newton going down, is bigger or the same or smaller than our maximum available maximum frictional force. How to calculate the maximum frictional force is by using this, the normal force multiplied by mu s. Our mu s is 0.2. So our maximum frictional force will be 0.2 multiplied by n here, 1093 Newton. It's supposed to be slightly above 200 Newtons, which means our frictional force here is lower than the maximum frictional force. In that case, what is actually happening there? What is actually happening? So in that case, the block that we are studying here is in the stationary mode. Okay, it stays stationary. And the frictional force, why? Because the frictional force is lower than the maximum available frictional force. Okay, actually say this here in the okay, in the discussion here. Yeah. So the calculation of the maximum frictional force is 219 Newton. Okay, and our force, frictional force is 134.3 Newtons going down. Remember, because it's minus, supposed to be the opposites of the current direction. So 134.3 Newtons going down. So that's our frictional force. And the condition is stationary because the frictional force is lower than our maximum frictional force. Okay, now let's try to solve for P. Okay, question B. Question B is if P is 100 Newtons, what will happen there? Okay, the free body diagram is still the same, but I replace 500 Newton with 100 Newtons like this. Sigma Fx is like this. 100 cos 20 plus F minus 981 Newtons sin 20 equal to 0. And sigma Fy equal to 0, it will be like this. N minus 100 sin 20 minus 981 cos 20 equal to 0. And the solution will be like this. This is the solution, the calculation, because it's two unknowns, two equations. So we can solve for it. So the frictional force there, the calculated frictional force is 242 Newtons. The direction is correct now. It's going up like this. It's going there, going up like that, 242 Newtons. And the normal force is 956 Newton. Okay, but the same here. We don't know whether this value, the frictional force here, the value here is correct or not. We have to see, because we have to know from those three conditions, stationary, impending motion, or motion. Between these three conditions, which is happening, which one is happening in this particular problem? Okay, in that case, what we're supposed to do, as usual, try to check with the maximum frictional force. The maximum frictional force is supposed to be N multiplied by the mu S, static coefficient of friction, 0.2. And by doing so, we know that the frictional force, the maximum frictional force, is supposed to be lower than 200 Newton. As you can see here, our calculated friction force is 242 Newton, which is higher than 200 Newtons. So in that case, it's not possible, okay? Because our frictional force is not supposed to be higher than our maximum frictional force. In that case, I know that this particular problem, the end results, the motion is happening, slipping is happening there, because frictional force higher than the maximum frictional force is not possible. Okay, so our free body diagram here is totally wrong. Okay, so we have to recalculate again and replace this F here, okay, with mu k multiplied by n. We have to replace this with mu k multiplied by n, and then after that, the equilibrium will not be there. And then the next thing that we can do is to find out the sigma fx, the total force in the x direction, and we can calculate for the acceleration using sigma fx equal to mass multiplied by acceleration. That's the thing. Okay, as you can see here, see our maximum frictional force is 191.2 newtons, which is lower than our calculated friction force, and it is not possible. Okay, that's why we have to recalculate our frictional force. Okay, it's supposed to be mu k multiplied by n, and the value is 162.5 Newton going up. That's the frictional force. Okay, so that's the problem, one of the problem. So this particular problem is the second condition where we don't know the condition from the beginning. Okay, I will give you another example here, this one. This is the example where we know that impending motion is happening. Why is like that? Because you can see here, the question here is if we have this kind of cylinder like that, homogeneous, and then the cylinder is have a friction with this particular wall and another friction with this particular wall. Okay, and the one in question here is determine the value of m which will cause the cylinder to slip. Okay, determine the value of m which will cause the cylinder to slip. Okay, we have to know that if we give moment less than the moment that supposed to make the things in an impending motion condition, if the moment is less than that, this particular cylinder will stay stationary. So in order for it to rotate, okay, in order for it to rotate, you have to give a moment at least is slightly higher than the impending motion case. So what we can calculate is the impending motion case. So the moment which caused the impending motion. And our result is supposed to be slightly higher than that. Okay, so let's try to draw the free body diagram. Remember, there is a contact here, there is a contact here, so there will be a normal force perpendicular to the ground here, normal force perpendicular to the ground, and frictional force parallel to the ground here, frictional force parallel to the ground there. And the friction force is supposed to be the opposites of the slipping direction. So this is our free body diagram. You can see here, because the moment is going clockwise, the frictional force is supposed to resist the rotation. In that case, means that it's supposed to give us the opposite direction of the movement. So in that case, if the movement is clockwise, the frictional force is supposed to be counterclockwise. So at this particular point, it's supposed to be going up. At point B, it's supposed to be going like this. That's the frictional force. And the normal force is supposed to be perpendicular to the ground, like this. Perpendicular to the ground, like this. And there is a mass as well, 249 Newton to 30 kilograms multiplied by 9.81 meter per second square. So this is all the things that we need. Moment, gravitational force, frictional force at A, normal force at A, frictional force at B, normal force at B. And remember, because from the beginning we know that the frictional force that we're supposed to use is supposed to be frictional force for impending motion. That's why I put it like this. Instead of just FA here, I put it as mu S multiplied by NA. So in this case, it is known value. Oh, I mean, not known value, but the unknown here is just NA. The unknown here is just NB as well. So actually, the number of unknowns that we have here is just NB, NA, and M. So only 3 unknowns, NA, NB, and M. Okay, and because this one is not a point equilibrium, so we have 3 equations: sigma fx, sigma fy, and sigma moment. Using sigma fx, okay, what we have there will be NA and NB and FB there. NB sin 30 plus 0.25 multiplied by NB, because this one 0.25 is actually our mu S multiplied by NB. This is our FB, frictional force at B. Okay, cos 30 degrees minus NA equal to 0. Then using sigma Fy, this is what we have: NB cos 30 degrees. Okay, then minus 0.25 multiplied by NB sin 30 degrees because of this one, and then plus 0.25 multiplied by NA is for this one, FA, this one. Okay, minus 294 equal to 0. And the last one is sigma moment. Sigma moment at the center equal to 0. What we have there will be moment. Counterclockwise is positive in this case. So minus M plus the radius is 0.2. Okay, so 0.25 NB is our frictional force at this point B, FB. FB multiplied by 0.2 and FA multiplied by 0.2. Okay, 0.25 NA here is actually FA. So we have 1, 2, 3, 1, 2, 3, 1, 2, 3 unknowns. So total is 3 unknowns. Total 3 unknowns, and we have 3 equations, so we can solve it. This is the solution. Our moment will be 22.9 Newton meters. That's the answer. Okay, I think that's all for today's explanation. Hope it helps you guys to understand about the friction, and I hope that it reminds you with what the things that you have learned before about friction. Okay, I think that's all. See you again.